All right, in section 5.2, we're going to talk about double integrals over general regions instead of just rectangles. Early on, um, there's sort of a clever extension of the double integral to rectangular regions just to take advantage of that definition that we learned in section 5.1. But really what we're talking about is being able to describe non-rectangular regions, sort of curvy regions in the domain, so that we can integrate over a wider variety of sets. The goals here are to be able to evaluate double integrals. That means setting up the integral, which is really the most important part. You've got some region that's described, and your goal is to develop a mathematical description of that region and turn it into an integral, and we'll talk a lot more about that. And then some applications are to use double integrals to calculate the volume of a region between two surfaces or the area of some kind of region in the plane, and then to solve problems involving improper integrals. I will say that I'm dramatically de-emphasizing that particular aspect of it. I want to talk a little bit about what an improper integral is in this new context, but I'm not going to be asking you to do any exercises related to them. All right, so the big ideas here are, rectangular regions are a great introduction to double integration, and in fact we use the rectangular region to define what a double integral is. But in this section, we're going to learn how to integrate over regions whose top and bottom boundaries are described by functions, or alternatively, whose left and right boundaries are described by functions. Even better, we can use properties of the double integral to take even more complicated boundaries. So maybe your boundary doesn't have top and bottom, maybe your region doesn't have top and bottom boundaries that can be described by functions, but maybe it can be chopped up into pieces that can be described, whose boundaries can be described by functions. So we'll see that. With this new observation, we can integrate over almost any kind of region. Just a note here that describing regions boundaries by functions is going to require you to be very comfortable with the common curves like lines, parabolas, trig functions, exponentials, and logs. And not only that, but translations of those functions, and practice is going to be important here, and review of those basic kinds of curves if you're a little bit uncomfortable with them. And then lastly, as I mentioned, though we'll de-emphasize it, we're going to talk about improper double integrals. And this is a situation where either the region of integration is unbounded or the function itself becomes unbounded on the region of integration, or both. All right, flyover here. So general regions of integration, like this pinkish region D, you can see it's got sort of this wavy boundary to it. How are we going to manage this? What we're going to do is, at least technically, since it's a bounded region, we're going to find a rectangle that contains that region. And if we're interested in integrating some function f over the region D, what we're going to do is extend f out to some enclosing rectangle by just making it 0 outside. So we let g of x and y equal f of x and y inside this region. And then we let g of x and y equal 0 outside of that region, and that's functionally equivalent to integrating over the region D, but it lets us leverage the definition that we set up in section 5.1 where we integrate over rectangular regions. So this is really a technical point, and it's just to put this idea of integrating over general bounded regions on a solid mathematical foundation like the one that we constructed in section 5.1. So know that in the background, all of that's going on, and what that lets us do is apply, for example, all of the properties of double integrals like linearity and upper and lower bounds to these irregular regions. And so that's what we see here, this definition. I'm sorry, up here, this definition of the function g as we extend. There are two kinds of regions that we'll study here, and sort of canonically. And a type 1 region is a region whose top and bottom boundaries are described by functions, and whose left and right boundaries are either vertical lines or just points. And a type 2 region is one in which the left and right boundaries are described by functions, and the top and bottom boundaries are either lines or points. And we do have some kinds of regions that are both. For example, if you look at this region, the left and, or this is two curves that sort of intersect. It's a type 1 region because its top boundary and its bottom boundary are functions, but one could also consider this a type 2 region because if we go horizontally, the right-hand boundary is a function of x, and is a function, and the left-hand boundary is a function. A big task for you during this section is going to be to decide which way I want to go. So lots of times there are choices, functions that are both type 1 and type 2, regions that are both type 1 and type 2, and you have a choice. And honestly, sometimes treating it as a type 2 region where you're integrating horizontally first is easier than treating it as a type 1 region where you're integrating vertically first. So double integrals over non-rectangular regions, here's the definition that I was talking about. We take f, we extend it out to the rectangle R by setting it equal to 0, and we get rectangular integration. Of course, we don't want to do that every time. That's the theoretical foundation. What we want to do is describe the region D using functions and integrate directly. Fubini's theorem applies here, so one can integrate a type 1, integrate it as if it were a region of type 1, where we go from the lower boundary to the upper boundary and then integrate over from left to right. Or we can treat it as a region of type 2 where we integrate from the left boundary to the right boundary and then from C to D in the y direction. Fubini's theorem, remember, says that you can do the integration in either direction, and that's still true here for general regions. Let's look briefly at looking at an integral over a type 1 region. So the figure in 516, where is that? That's this guy here. So this is, I'm sorry, no it isn't. Just go jump to it. Gosh, where even is that figure? I don't know. Okay, let's just see the solution. Okay, so here's a figure 516, and we're integrating over this non-rectangular region, and we're integrating x squared e to the xy. We'll treat it as a type 1 region, which means we need the equations of the upper and lower boundaries, and we're going to integrate vertically first. That means we're integrating in the y direction first. So in the y direction, a vertical slice of this region starts on the curve 1/2 x down here and ends on the curve y equals 1 up here. So integrating with respect to y, the y limits of integration go from the bottom curve to the top curve always. And then what do you do to set the limits of the integration with respect to x? You just integrate over the span of this set. This set lives between x equals 0 and x equals 2. Another way to see this is if you just took this region and smushed it down onto the x-axis, what interval would it land on? It's going to land on the interval from 0 to 2, and that's the limits of integration here. And then now that you're you've got the limits of integration, you integrate with respect to y first and plug in these limits, and it doesn't matter that the limits involve variables like the variable x. You plug them in as you normally would, you subtract, and what's left behind is a function solely of x, which you're now ready to integrate with respect to x. Conducting that integration, you end up with 2. You could also do this as a region of type 2, and then you would be integrating horizontally first in the x direction, so the inner integral would be with respect to x. And then if you smushed this whole region onto the y-axis, what would the limits of integration be? They would go from 0 up to 1, y equals 0 up to 1. And you'll definitely be expected to do that. I should warn you that it's not simply a matter, there's not any kind of real recipe for interchanging the limits of integration. You have to go back to the figure and rethink the whole process in the other direction in order to generate these new limits of integration. So this is the exact same integral and will result in the exact same value, but notice that the limits of integration are very different. I'd love to give you a recipe, but there is no recipe. Go back to the original region, integrate in the other direction, and construct the limits of integration. Okay. As I mentioned before, not all regions are type 1 or type 2. Sometimes they're neither. And I can give you an example of that over here in the notes. An example of a region that's neither type 1 nor type 2 might be, I don't know, say this crescent-shaped region. Right, you're looking for a top and bottom curve, but there really isn't one. But that's okay, because we can take this thing and we can cut it right here. And I don't know, maybe we'd have to cut it right here. Do a little bit of surgery in this direction here, and maybe a little bit of surgery down here in this direction. But we could cut it up into enough pieces where we would get type 1 or type 2 regions. Maybe this guy needs to be like this, so this would be type 1. This might be type 2. What's this guy going to be? This is going to be type 2. And last, this will be type 1. So we always have the option of cutting up a complicated region of integration into type 1 and type 2 regions. And then what do? You just integrate all of these pieces and then add them together. So the total double integral over the general region, which we're using D for, would be the sum of all of those pieces. All right. So that's what this theorem is all about. And it's important that we chop up the region into pieces that are non-intersecting except that they're boundaries. And that's what's going on here. These are all non-intersecting pieces, and the only place they intersect are at the boundaries. You don't want to have them overlapping more than that, because then you're going to be double counting part of the integral, and that's not good. So that's what theorem 5.5 is all about. You can take a region that's neither type 1 or type 2, and you can chop it up into pieces that are type 1 or type 2 and then add them together. So here's an example. I'll let you look at that. Changing the order of integration, as I suggested earlier, many shapes are subject to this kind of changing of order of integration, and sometimes it's to your advantage to do so. Sometimes you switch the order of integration and you get an integral that's doable versus one that's not doable. So we'll talk about that. There's no real recipe for changing the order of integration. It always involves sketching the region and moving from, say, vertical slices to horizontal slices. Calculating volumes, areas, and average values. So the volume is really just the integral, right? You integrate over a region, and the integrand is the surface above the region, and by default it's adding up all those little rectangles in the limit, and you're getting the volume underneath the surface above the region. Areas, you just do the double integral of the constant function 1, and that's going to add up to the area of the complicated region. And finally, average values, you integrate the function f over the region and you divide by the area of the region. So these are all ideas that we learned in section 5.1. We're just going to apply them in the context of general regions of integration. All right, so for example, here's a region that's bounded by the function y equals 2x and the function y equals x squared. And we have a choice, right? This is a region that's both type 1 and type 2. We could choose to integrate with respect in the y direction first, in which case we would have an inner integral with respect to dy, or we could choose to integrate horizontally, and then the inner integral would be with respect to x. In the case of integrating as a type 2 region, where the inner integral is dx, we would have to solve for x in terms of y and use those as the limits of integration. All right. This is the area, the average value formula, which we'll do an example of. Again, the average value is really just a matter of setting up the integral and then dividing by the area of the region. Okay, improper double integrals, not going to dwell on this, but sometimes you've got a region that's unbounded, right? Or you've got a place within a bounded region where the function f is blowing up. For example, this is an unbounded region. It's the collection of points x minus y, absolute value x minus y greater than 2. That's an unbounded region. It doesn't fit inside any circle. Or this guy where you've got the potential of dividing by 0. In either of those cases, what you have to do is set up the integral really carefully with a limiting process. And there are two ways of doing this. One is to construct a bounded region where the boundaries are variable and you send the boundaries off to infinity. Or in the case of a place where the function's blowing up, what you do is you carve out a little region around the place where the function is blowing up, and then you compute that integral, and then you let the region around where the function is blowing up, you let that go to 0, let it collapse down on the point, and hope that something nice happens. We're not going to be doing any of that in this class, but it's nice to know that it's there. The last big topic is probability density functions. This is an extremely important application of double integrals, but it's one that we're not going to explore in this class. You would encounter this in an upper level probability class. All right, moving on to the exercises. This is a really skills heavy section. Do as many of these problems as you can make time for. Okay, in exercise 66, you're simply asked to identify the kind of region. And remember, a type 1 region has its boundaries above and below as functions. A type 2 region has its left and right boundaries as functions. Here, this is a type 2 region because it's bounded on the left by this parabolic shape and bounded on the right by this circular shape. So it'll be easy to construct the double integral in the horizontal direction. And so that means we would be integrating with respect to x first, exactly. So in problem 67, you're asked to actually do that integration. And we'll do that in the direction that we just described. That doesn't mean that we couldn't do it as a type 1 region, but we would need to chop it up into two pieces and then do this one and add them together. So we could do it, but it's this figure sort of naturally falls into a type 2 situation. All right, so in the type 2 context, the integral over the region D, f of x and y, dA, becomes, all right, we're integrating horizontally. We're integrating from the left boundary to the right boundary. On the left boundary, the lower limit is x equals -1 plus y squared, -1 plus y squared, up to the right boundary, x equals the square root of 1 minus y squared, square root 1 minus y squared. Now, if we took this figure, oh, and I'm sorry, and we're integrating xy plus 1, and remember, when we're integrating a type 2 region, we're doing dx first, so the inner integral is with respect to x. Okay, what are the outer limits of integration? Take this figure and smash it down vertically onto the x-axis. So just vertically smash it down onto the x-axis. What part of the x-axis is going to be covered if we smash it down onto the x-axis? Well, if you look closely, you can see that it's going to cover the interval from -1 to 1. So the limits in that direction, oops, I'm sorry, this is a type 2 region. Okay, start over again. We want to smash this thing onto the y-axis. We want to figure out the limits in the y direction. So we take this thing and we smush it horizontally onto the y-axis. What's it going to cover? It's going to cover the interval from -1 up to 1. So we'll put a -1 as the lower limit and a +1 as the upper limit. Remember that when you're constructing these integrals, it's always increasing. It's from the lower value to the higher value, always. If you reverse them by accident, you're going to introduce a minus sign that you probably don't want. All right, when I'm doing double integrals, I typically look at the inner integral. I always look at the inner integral first. So I'm going to do the inner integral, -1 plus y squared, square root of 1 minus y squared, xy plus 1 dx, like that. Alrighty. Integrating this integrand with respect to x, we get 1/2 x squared y plus x. And we want to evaluate those between the limits -1 plus y squared up to the square root of 1 minus y squared. Everywhere we see an x, we're going to replace it with the limits, so we get 1/2. Plugging in the upper limit, 1 minus y squared times another y plus square root of 1 minus y squared minus the quantity 1/2 -1 plus y squared y minus -1 plus y squared. Okay, if you expand all of that stuff out and simplify it, you get, I've got this in my notes here just to save time, we get -1/2 y to the 5th plus 1/2 y cubed minus y squared plus 1, and then we have that square root out there, plus 1 minus y squared. This is the result of the inner integral. We now go on to the outer integral, and that's with respect to y. So we're going to integrate in the y direction from -1 to 1. The integrand is -1/2 y to the 5th, 1/2 y cubed minus y squared plus 1 plus this oddball square root term, which we're kind of stuck with, like that. I'm going to break this up because one of these integrals is relatively easy and one of these is going to perhaps require a bit of review of Calc 2. So I'm going to take advantage of that to walk you through a bit of review of Calc 2 where we're going to do the square root integral via trig sub. So I'm going to take all of this polynomial stuff in y and call that an integral, and then I'm going to do all of the stuff under the square root and call that a different integral. If I do the stuff that's polynomial, I'm going to leave that to you. These are just polynomial integrations. We plug in 1, we plug in -1. What we're going to get is 4/3. So I'll leave that to you to check. Let's look at the other integral and review a little bit of our trig substitution. So -1 to 1, square root of 1 minus y squared dy. So we're going to take advantage of the Pythagorean identity here and let y equal sine of theta. So let's let y equal sine of theta. Then dy is cosine of theta d theta. Hopefully this is coming back to you. And we are going to substitute sine in for y. So we get 1 minus sine squared theta. And what's dy? We'll replace dy with cosine theta d theta, like that. What are the new limits of integration? So if y is equal to -1, what's the sine of theta? A good choice for this, if we go back to the unit circle, we know that we know that sine of theta is -1 down here and 1 up here. And if we kind of go around in this direction, increasing theta, remember, we're going to go from -pi/2 to pi/2. So the new limits of integration are -pi/2 to pi/2. It's convenient to change the limits of integration so that you don't have to change them back at the end. All right, 1 minus sine squared theta is secretly cosine squared theta, and we take the square root and we get the absolute value of cosine squared theta. Sorry, we get the absolute value of cosine theta. And we have another cosine of theta. Now, we might ask ourselves, do we need the absolute values in this particular case? And the answer is no, because if we look at the unit circle over here, while I'm going from theta equals -pi/2 up to pi/2, the cosine is staying exclusively over here on the positive x-axis. So there's no reason to keep these absolute values. Oops. And we have 2 cosines, so in fact we could just replace this with cosine squared. Cosine squared theta d theta, like that. Now you need to know a trig identity. You need to know that the cosine squared theta is 1/2 1 plus cosine 2 theta. Now I'm not asking you to memorize a whole lot of trig identities, but this is one that you need to memorize because it comes up often when you're integrating sine and cosine squared. All right, so we can replace that cosine squared with 1/2 1 plus cosine 2 theta. And now we finally have an integral that we can calculate after a trig sub and a trig identity. So we integrate, we get theta plus 1/2 sine 2 theta. That's the antiderivative of cosine 2 theta. And we're evaluating from -pi/2 to pi/2. Now, if I plug pi/2 and -pi/2 into the sine function, in both cases I get 0, so this doesn't matter. And if I plug pi/2 in for theta and subtract a negative pi/2, I get pi. So this whole integral nets out to pi/2. And don't forget where we started. We were trying to calculate this much larger integral. We calculated the first piece to be 4/3, and the second piece to be pi over 2. And so after all of that, the integral of xy plus 1 over this region, this type 2 region, is 4/3 plus pi over 2. All right. Hopefully that was a nice review of trig sub and also a good introduction to double integration over a region of type 2. Let's keep going. I've got a lot of examples here for you. As I suggested, do as many of these things as you can afford the time for, because this is a heavily skills-based section. All right, always start with a sketch. If you're not given a sketch, generate a sketch. So you're asked to integrate this function in problem 74 over the region D. So we're always looking at something like this. This is the abstract representation of the double integral. It's up to us to figure out what the limits of integration over here and whether this should be dx dy or dy dx. The only way really to figure that out is to sketch. So sketching this region, we see that x goes from 0 to 1, and y goes between x cubed and x cubed plus 1. So let's plot x cubed. That looks like this. And x cubed plus 1, I'm just going to kind of shift this whole thing up. All right. So it's the function x cubed, which again you should have memorized, and then x cubed plus 1 is that whole function shifted up 1 unit, and that's, shifting, translating functions, that's another thing that you should be familiar with. And then we're going from x equals 0 over here to x equals 1. I'll just put it right here, and this is the region that we're interested in. What kind of region is this? Type 1 or type 2? It's type 1 because the top and the bottom are curves and the left and the right are straight lines. So we're going to integrate this in the vertical direction first. That's dy and then dx. So dy dx, just to remind us, the inner integral, the inner limits of integration go from x cubed, the lower curve, up to x cubed plus 1, the upper curve. Now if you took this shape and you smushed it down onto the x-axis, right, you smushed it down, collapsed it down onto the x-axis, what would it cover? It would cover the interval from 0 to 1. That's also clear just from looking at this part of the definition of the domain. So the limits in the x direction are 0 to 1 and 2x plus 5y. To be honest, I'd be super excited if you could reliably build a double integral like this. I want you to be able to calculate these integrals by hand, but this is something that you can also do in Sage. So let's calculate this integral by hand. The inner integral, in this case it's a type 1 region, so we're integrating with respect to y first. The inner integral to xy plus 5 halves y squared, and we plug in y equals x cubed and y equals x cubed plus 1. I've got this in my notes somewhere. It's going to turn out to be 5x cubed plus 2x plus 5 halves. And I just got that by substituting in for y and expanding and simplifying as much as possible. We move on to the outer integral. That's the integral from 0 to 1 of the inner integral, 5x cubed plus 2x plus 5 halves dx. And the outer integral, same thing, just follow your rules of integration and plug in 0 and 1 and you get 19/4. So I'll leave that to you to double check, practice your by hand integration skills. It would be hard to do this in the other direction, and that's because if we go in the other direction, say this way, we're going to encounter kind of issues here and here where the left and right curve changed their definition. Doesn't mean we couldn't do it. We could divide this up into 3 regions and just integrate them as type 2 regions and then add them together. But it would be a lot of work. It's much easier to just integrate this as a type 1 region where we have a single upper curve and a single lower curve. These are the kinds of things that you need to pay attention to when you're deciding whether to do it as a type 1 region or a type 2 region. All right, exercise 78, same thing. We want to find the integral of this function, f of x and y, over the region D. So we don't have a sketch, so let's construct a sketch. And we'll put these points, 0, 0, 0, 3, and 3, 0 onto our graph. And this defines the region D. This is a region that's either type 1 or type 2, so you get to just make a choice. Let's do it as a type 2 just to kind of do some practice there. I don't want us always fixating on doing it as a type 1 region. So if we're going to do it as a type 2 region, we need to find the equation of this curve. And that's simply a line. And it's a line that goes through the point 0, 3 and 3, 0. So you have 2 choices here. You can kind of just use your experience with lines. So for example, if you make a guess y equals 3 minus x, if you plug in x equals 0, you get 3, which hits the top vertex. And if you plug in x equals 3, you get 0. That's the other vertex. So in fact, that's the right choice. If you're unsure about that, you can go through the process of computing the slope. The slope here is going to be, let's see, negative 3 over 3, aka negative 1, and then use the point slope form. So I'll leave that to you. Here we get y equals 3 minus x. If we're going to do this as a type 2 region, then we need to solve for x in terms of y. And in that case, x is equal to 3 minus y. Great. All right, as a type 2 integral, let's set up the limits of integration. We're integrating horizontally, so we're going from the left curve to the right curve. What's the left curve? The left curve is x equals 0, and the right curve is x equals 3 minus y. What's the integrand? It's sine y. When we're integrating horizontally first as type 2, we're doing dx first. The outer limits of integration, that's dy. What would you get if you smashed this region onto the y-axis? You would cover this interval on the y-axis, and that interval goes from 0 up to 3. So the outer limits are 0 to 3. Let me write those in black. And we've successfully constructed the integral. Once again, I can't emphasize enough, this is the really important step. If you can construct the double integral, I'm really happy. And if you make a few mistakes computing the integral, I'm less concerned about that. Again, you want to get good at that. You want to become skilled because in lots of contexts, it's easier to just do it by hand than to go dig up a computer. But and the other thing is, being able to do it by hand develops that intuition, and it gives you a good skeptical eye on what a computer might be generating, and it helps you catch mistakes in a computer calculation. The inner integral, that's with respect to x. So inner integral, integrating sine of y with respect to x is just x sine y, evaluated from 0 up to 3 minus y. Plugging in 3 minus y for x, don't forget that which variable you're substituting for. So we get 3 minus y sine of y. Plugging in 0 and subtracting, we get 0, so we're fine there. All right, the outer integral. So we take the result of the inner integral and we integrate from 0 to 3. Like that. Okay, and let's see, we're on problem 78 here. Hold on, I'm going to get a sip of water. My voice is kind of leaving me. Okay, let's keep going here. So how do we do this integral with respect to y? Here's another bit of review for integration from Calc 2, integration by parts. Let's let u equal 3 minus y and dv equal sine y dy. So everything's on the table here when you're doing these kinds of calculations. The derivative here is negative dy, and the antiderivative here is negative cosine y, like that. So this integral is u times v, 3 minus y, times minus cosine y, minus the quantity v du. Oops, and I have to remember to evaluate this from 0 to 3, minus the quantity from 0 to 3 of cosine y dy, like that. Let's try to evaluate these boundary terms first. If I plug in 3, I get 0, and if I plug in 0, I get, 3, I guess. So this works out to be 3. And we still have to do this integral over here. The integral of cosine y is sine y, so we get minus sine, we get 3 minus sine of y from 0 to 3. Looks like that's going to be 3 minus sine of 3. Let me check my notes here. That looks good. Now, something I noticed as I was going along here is we decided to do this as a type 2 integral, really just for the heck of it. Let's do this as a type 1 integral, and you're going to find that it's actually a little bit of an easier process. So I'm going to write here as type 1. So here we need to reverse the order of integration. So we go up to the original figure and we start looking at it in the other direction. So let's say we want to integrate vertically first, from the bottom to the top. So that means we're integrating with respect to y first. Let me change back to black here. Integrating with respect to y first, and what was the integrand again? Sine y. What are those limits in the y direction? We start out at y equals 0, and we end up on this upper curve y equals 3 minus x. Y equals 0 to y equals 3 minus x. And now if we took this figure and we smushed it down onto the x-axis, we would cover this part of the x-axis, which goes from 0 to 3. So that outer set of limits is 0 to 3. So similar looking, and I'd like to tell you that there was some kind of method here, but there's not, because it's, like here it looks like, oh, I just changed this y to an x, but that's more to do with there's an overwhelming amount of symmetry in this figure. But other figures, other regions of integration aren't so nice. So you always have to go back to the figure when you're reversing the order of integration. Start from scratch and rebuild the limits of integration. There are no shortcuts. Let's talk about the inner integral. The inner integral is with respect to y, the outer integral is with respect to x. Integrating the inner integral with respect to y, what do we get? Negative cosine y from 0 to 3 minus x. Plugging in and subtracting, we get minus cosine 3 minus x plus 1, like that. Alrighty, that's the inner integral. Let's look at the outer integral. So now the outer integral is with respect to x, and we just want to integrate this with respect to x. We get x, what? Oh gosh, so many minus signs. Plus cosine 3 minus x. Sorry, plus sine 3 minus x. Let me see if I believe that. Yes, I believe that. And I'm going to go from 0 to 3. I'm going to plug in 3, and I'll get 0, because 3 minus 3 is 0, sine of 0 is 0, minus, plugging in 0, I get 0 here, sine of 3 minus 0 is sine of 3, and we get the exact same result, but notice there was no integration by parts. This is one of the lessons that I was describing to you earlier. Sometimes if you reverse the order of integration, you can get an easier integration process, or even better, in one direction you literally can't do it, and in the other direction you get a u substitution or something and things work out. So there are reasons for being able to reverse the order of integration. Sometimes you can turn a hard integral into an easy integral, or an impossible integral into a doable integral. All right, let's do a couple more of these. Again, very skills-based section, a lot of practice here. In problem 84, you're just asked to evaluate this particular integral, and it looks horrible, but let's just start cranking away and see what happens. So we're going to do the inner integral. That's integrating this with respect to x, so it's x squared plus x to the fourth, and then plugging in minus the square root of 1 minus y squared to plus the square root of 1 minus y squared, like that. Now if I plug these in, I get 1 minus y squared plus 1 minus y squared squared minus, plugging this in, 1 minus y squared plus 1 minus y squared squared, which is 0. And I might have figured that out anyway, because the upper and lower limits are just negatives of each other. And these are even functions. X squared is an even function. X to the fourth is an even function. Look at an even function over a symmetric interval like that, you're going to get 0. The inner integral turns into 0. The outer integral, you can probably guess, but let me just sort of leave no doubt. We want to integrate 0 with respect to y. An antiderivative of 0 might be a constant, c. And we integrate c from 0 to 1. We plug in 1, we get c. We plug in 0, we get c, and we get 0. It's not necessary to go through all of this just to establish that this is 0. If you integrate 0, the definite integral of 0 over any interval is 0. So this particular this particular integral is 0. Something that's useful, it's not required here, but can you look at these limits of integration and sketch the region of integration? The answer is yes, and it's something that you should become skilled at. Here we have x is equal to square root of 1 minus y squared, and x equal negative square root of 1 minus y squared. So let's look at those limits of integration and see if we can't make a sketch. So again, not required here. X equals square root of 1 minus y squared. If we square both sides, we get x squared equals 1 minus y squared, or x squared plus y squared equals 1. This is the unit circle. Like that. All right. We are integrating here with respect to x, so we're doing horizontal integration, a type 2 integration like this. And we're supposed to do this from y equals 0 to y equals 1. So where is that? Well, that's these are all 1's going around here. 1, 1, minus 1, minus 1. We're integrating from 0 to 1. That's here. So we're doing these horizontal slices over the y interval from 0 to 1. That's this upper half of the unit circle. So the region of integration in this case we can discern from the limits on the integral. You should be able to go in both directions. Given a figure, generate the limits. Given the limits, generate the figure. You should practice going in both directions, even if it's not explicitly asked for in the exercise. In problem 88, you're asked to show that this double integral is equal to this sum of integrals by dividing the region D into two regions, where D is given by this expression. So this is an example of that decomposition process that we talked about during the flyover. So let's sketch the region D. The region D is given by three conditions. It's hard to kind of pick them out here. You really have to pay attention to the commas. There's a comma here and a comma here. So we've got three conditions here. The first condition is that y is greater than or equal to x. So let's sketch the function y equals x. There's y equals x. And we're talking about everything above y equals x. We also want the region or the condition that y be greater than or equal to negative x. So let's sketch the function y equals negative x. And look at everything above that. And then finally, we want the condition that y be less than or equal to 2 minus x squared. What does 2 minus x squared look like? Well, break it down. Minus x squared is the parabola opening up. Minus x squared is that same parabola opening down with its vertex at the origin. And then adding 2 moves that whole thing up 2 units. So we're talking about a parabola that's shifted up 2 units and everything that's below that parabola. Now, if we're going to satisfy all three of these conditions, we're looking for the intersection of the black set, the green set, and the blue set. Where is that? That's right here. That's the region that we're interested in. All right, now that we have a pretty good idea of the region, let's look at this identity that we're asked to prove. The identity is involving dy dx. So we're looking at doing vertical, integrating vertically first. The inner integral is parallel to the y-axis. And we see that we don't quite have a type 1 region. The region is kind of split into two type 1 regions, or can be divided into two type 1 regions. And the reason for that is the bottom curve here changes. It goes from being the curve y equals minus x on the left-hand side to y equals plus x on the right-hand side. And if we just stayed to the left of the y-axis or stayed to the right of the y-axis, these would be lovely type 1 regions. But together they're not type 1 regions. So we break it up and we start writing out these integrals. I'm running out of colors here, but let's call this this region A and this region B. So the whole integral over this region, f of x and y, dA, is going to be the integral over the region A plus the integral over the region B, and I'm just not writing it all out, but that's kind of what we would do here. So let's look at the region over A. And what do we have, y squared? Yeah, y squared. dA, like this. All right, so if we're going to do the region A and we want to integrate with respect to y first, we're going from the lower curve, which is minus x, to the upper curve, which is 2 minus x squared. And then if we smash this onto the x-axis, what would it cover? Oops, well, we've got to figure out what's that point right there. We've got to figure out where these two curves intersect. So we look at 2 minus x squared, and we set it equal to minus x. Let's move everything over to the right-hand side. And we get something like that. All right, we can factor this. This is x minus 2 times x plus 1. So there are two solutions. X equals 2 or negative 1. Which one do you think we're looking for? This must be the negative root, negative 1 out here. So we've just figured out that if we took this figure and we smashed it down onto the x-axis, it would cover this part of the x-axis. That helps us determine the limits along the x-axis, 0 to negative 1. Oops, and I've always got to put the smaller number at the bottom. Negative 1 to 0, y squared dA. I'm going to leave it to you to do that calculation. I've done it in advance here, and it's actually surprisingly hideous. I ended up using Sage for this, 673 over 420. 673 over 420. All right. What about the integral over region B? Let's write that one out. Y squared dA. All right, over region B, we're going in the vertical direction from y equals x up to y equals 2 minus x squared, so to x to 2 minus x squared. And what's the outer limit of integration? Same thing. We want to collapse b down onto the x-axis. By symmetry here, although you can check algebraically if you want, this is plus 1 right here. So the outer limits of integration go from 0 to 1, y squared dy dx. This also works out to 673 over 420. And we shouldn't be surprised that it's the same, because the region of integration is symmetric about the y-axis, and so too is the function. F of x and y equals y squared. That's also symmetric about the y-axis. It doesn't matter, it doesn't depend on x, so it's symmetric about the y-axis. So taking those two things into account, we could have predicted that the integral over the region A would equal the integral over the region B. What's the total integral? The total integral is just 2 times 673 over 420, which is 673 over 210, whatever that means. All right, and exercise 92, you're asked to find the area of the region D. And we're given the region again as a collection of conditions. Again, you have to have a sharp eye and look for these commas. There's a comma here, and a comma here, so there are actually 4 conditions. And all of these conditions need to be met simultaneously in order to be a member of the set D. So we're going to sketch first. And we'll just go through each of these conditions and try to figure out what the intersection is. So we have y is greater than 1 minus x squared. So remember, x squared is this, minus x squared is this, and then 1 minus x squared, shift the whole thing up 1 unit. So we'll get ourselves something like this. All right. And then we have y less than or equal to 4 minus x squared, so that's up here. Like that. Okay, so that takes care of those two, the first two. We have y greater than or equal to 0. Where's that? That's anything above the x-axis. And we have x greater than or equal to 0. That's anything to the right of the y-axis. All right, so I have to be above this curve. I have to be below this curve. I have to be above the x-axis, and I have to be to the right of the y-axis. Intersecting all of those conditions at once gives us this region. All right, is this a type 1 region or a type 2 region? Trick question. It's neither. So we have to decide how we're going to attack this problem. I'm going to divide this strategically right here. And if I do that, I get two regions, both of which are type 1. So the green line divides this into two regions, A and B, that are both of type 1. So the whole integral, finding the area of D, what integral are we talking about? We're talking about the integral over the set D of the number 1 dA is going to equal the integral over the region A dA plus the integral over the region B of 1 dA. So now it's our job to figure out how to put limits on these integrals and calculate them. All right, for set A, we're going from the lower parabola to the upper parabola, and we're doing it as a type 1, so that means we're integrating with respect to dy. Y starts out on the lower parabola, 1 minus x squared, and goes up to the upper parabola, 4 minus x squared. We're integrating 1 dy. And then if we take this set and we smash it down onto the x-axis, take this set and smash it down onto the x-axis, what is the range of x values? It goes from 0 to 1. How did I figure that out? That's where this parabola 1 minus x squared is equal to 0. 1 minus x squared equals 0. Solving for x, we get plus or minus 1, and we'll take the positive 1. All right, so that's the setup for the integral over A plus the integral over B. All right, in the region B, we start down here at the bottom and we go up to the top. What's the equation of this bottom curve? It's y equals 0. What's the equation of the top curve? Same as the other one, 4 minus x squared. If we take this region and smash it down onto the x-axis, it's going to cover this segment. And that's the segment from x equals 1 to x equals 2. And we're integrating 1 dy dx. Now we're left with a relatively straightforward pair of integrals. I've actually taken the liberty of doing these off to the side, and I got, what did I get? I got 14/3. So maybe a chance to do some practice integration, and you can check your answer against mine. So that's an example of taking a region that was neither type 1 nor type 2 and breaking it up into two type 1 regions. There's no reason that I had to do a vertical slice here. I could have done a horizontal slice as well. The reason I didn't do a horizontal slice is I could see in advance that when I go horizontally and I solve for x in terms of y, I'm going to introduce some square roots, and that may give me harder integrals. All right, in 104, we're asked to find the volume of the solid under this plane above the region bounded by x equals tan y and x equals minus tan y and x equals 1. So we have, again, three conditions that describe the region D. We have to make a sketch in order to build these integrals. Really got to kind of dredge up some of your pre-calc here. what does x equals tangent y look like? What I want you to do is just imagine the other, this is how I do it anyway. I get a grip on first, what does the tangent function look like? And you may or may not remember, it goes from, a branch of it goes from minus pi over 2 to pi over 2. And it goes through the origin, and then it has these vertical asymptotes here and here at pi over 2, because that's where the cosine goes to 0. And we might remember that the tangent of x is equal to the sine of x over the cosine of x. So we're going to get, at least on that, on one branch, get something that looks like this. Of course, you may also recall that it repeats like this, but we're just going to look at that middle branch. So x equals tangent of y. We're going to get something, right? We've got x in terms of y instead of y in terms of x. So we've got to take that plot that we just sort of reminded ourselves about and transpose it, put it in the other direction, and kind of figure out where it should be. So I'm going to put my pi over 2 here, and I'm going to put an asymptote here, and put a minus pi over 2 down here, and an asymptote here. And I'm going to then recognize that x equals tan y is just this middle curve over here translated onto its horizontal form. And of course, x equals minus tangent of y is just the reflection of this curve over the x-axis. Oops. Be careful drawing these. All right. So just to remind everybody, the top curve is x equals tan y, and the bottom curve is x equals minus tan y. Okay, the region bounded by these curves, we have one curve left, x equals 1. So let's put x equals 1 in here. And we now see the region that's bounded. All right, what kind of region is this? We want to do the volume under the plane described by the function x minus y. So we are looking at a double integral. Let me change over to black. Of the plane x minus y dA. We're going to treat this as a type 1 region because it's obvious that we're going to go from the bottom curve to the top curve like that. So we're integrating with respect to y first. The lower limit, if we're integrating in this direction, is the minus tan function, and the upper limit is tan of y. I've got to be careful here. I've got to solve for y in terms of x. That's unusual. Okay, so solving for y in terms of x, y equals arc tan x, and y equals minus arc tan x, like that. Alrighty. So go from the lower curve, yes, minus arc tan x to the upper curve arc tan x, and we are integrating x minus y, and we're doing that with respect to y first. And then what are the outer limits of integration? Take this thing and smush it down onto the x-axis, and what's the range of x values? They go from 0 to 1. Oops, that outer integral is dx. All right, I've done this one in my notes also. Let me see if I can find them here. All right, so I think here's another example of an integral that's really hard in one direction and perhaps a little bit easier in the other direction. So when you do this integral, you're going to start getting expressions involving the arctan, and the antiderivative of arctan is not one that I expect you to have memorized. So maybe this suggests treating as type 1, but we might actually have an easier time doing this as two type 2 integrals. So let's try this as two type 2 integrals. To avoid the arctan. All right, so as two type 2 integrals, we're going to chop this thing up right here along the middle, and we'll use this as A and this as B. So as two type 2 integrals, we're going to integrate the region A. All right, in that direction, we're going to go from the lower curve to the upper curve in the horizontal direction. The lower curve is tangent of y, and the upper curve is 1. And then if we take this thing and we smash it down onto the y-axis, what is, if x is 1, what's y? You might remember that's pi over 4. That's where sine and cosine are equal. So if we smash this down onto the y-axis, we're going to stop here at pi over 4. So the limits here are 0 to pi over 4. And the integrand, of course, is the same, x minus y dx dy, plus the integral of region B, the lower curve being minus tan y, the upper curve still being 1, and the outer limits of integration are going to be from minus pi over 4 to pi over to 0, excuse me, minus pi over 4 to 0, x minus y dx dy. Okay, when you do this integral, you're going to get slightly nicer results. You're going to get tangents and tangents squared, but things are going to work out nicely. And I'll leave that to you as a review of a little bit of trig integration. And we could jump over to Sage, for example, and check the resulting calculation. Maybe I'll walk you through that really briefly. So let's jump over to Sage. And we'll create, we'll do this integral in a new worksheet. So let's create a new worksheet. And what exercise are we actually working on here? We're doing 5.2.104. And this is a Sage worksheet. All right, let's try to type these integrals in. Let's do the first one. So we're going to integrate, a double integral, excuse me, integrate. And the integrand is x minus y. And we're going to integrate with respect to x first. And we're going to go from tangent of y up to 1. And then we're going to integrate in the y direction from 0 to pi over 4. All right, let's see what that gives us. Oh, I forgot to declare y. Let's go up here. I think x is declared by default in Sage, but y is not. Oh boy, I have no idea what any of that is. Catalan, some sort of exciting random function, I suppose. And then we can do the other integral. My guess is this would work out nicely if we had if we were doing it by hand, but at this point I'm just going to kind of, so minus pi over 4. Up to 0. I think that's all we need to change. Let's just double check. Minus tangent of y, up to 1, minus pi over 4. All right, let's see what that looks like. Yes, I had a feeling they might cancel. So if we take these two guys and add them together, we might get something nicer. There we go, pi over 2 minus 1. All right, so using Sage, pi over 2 minus 1. We should certainly, so let me make a note here using Sage. We should certainly ask ourselves, does this seem like a reasonable answer? If we look at x minus y on this region, it looks like x is bigger than y on this whole region. This is probably positive on the whole region. And so, and this also is positive. Pi over 2 minus 1 is positive. So yeah, I think we're okay here. All right, problem 107. This is a more theoretical problem. Don't let them scare you. Show that the volume of the solid under this surface G prime and above the region bounded by these conditions is given by this expression. All right, so let's sketch the region. We don't really know what this region looks like, but we can kind of sketch in some proxies. So we're given that g is a positive and increasing function on the interval from a to b. I don't really care what it looks like other than that it's above the x-axis and it's increasing. So it's going to look something like that. And then we're also going to look at the curve g of x plus k, where k is a positive real number. So that means take this increasing guy and move it up by a distance of k, like that. And then we're going to bound it on the left by x equals a, bound it on the right by x equals b. And we now see this sort of generic region that's being described. This is the region D, and we want to compute the double integral of g prime of x over this region D. This looks like a region, a type 1 region, so let's treat it as a type 1 region, which means we'll integrate with respect to y first, and then with respect to x. The limits in the y direction go from the lower curve, g of x, to the upper curve, g of x plus k. And if we took this region and smushed it down onto the x-axis, what interval would we get? We would get the interval from a to b. So we've now successfully built this integral. It turns out we can actually do a little bit of this integration. The inner integral we can integrate this with respect to y, right? It's just g prime of x times y evaluated from g of x up to g of x plus k, like that. Sorry, careful with my parentheses here. Plugging those two in and subtracting, we get g prime of x, we get g of x plus k minus g of x. That nets out to just k. And now we can do the outer integral. The outer integral is the integral from a to b of k g prime of x dx. And it turns out we can actually do this one using the fundamental theorem of calculus. An antiderivative of g prime is just g, and we can evaluate from a to b. K g of b minus g of a, and that is in fact the result that we were looking for. These kinds of calculations where you don't have explicit functions but you have sort of derivatives of functions and properties of functions. This is the more usual way that we apply calculus and mathematics in more advanced courses, and we get these sort of interesting results. Okay, in exercise 116, we've got this region bounded above by sine of x and below by y equals x to the fourth. You're asked to find a graphing calculator to find the intersection points, because this intersection point right here is where sine of x equals x to the fourth, and we can't solve this explicitly. So we're going to need that though, because we're going to need it as one of our limits of integration. So for now, let's let that solution be, let gamma solve this equation. So we'll call this gamma right here. And then we'll just do the whole problem in terms of gamma, and at the end we'll figure out what gamma is and get an explicit result. This is a region of type 1 or type 2. I think for the sake of not having to solve for x, I'll treat it as a region of type 1. So doing that, I get the integral over d. What am I integrating here? I'm trying to find the area. I'm trying to find the area. So I'm just going to integrate 1 dA. As a type 1 region, I'm going to integrate 1 dy dx. The inner limits of integration go from the bottom curve, x to the fourth, to the top curve, sine of x. And if we took this whole region and smushed it down onto the x-axis, we would cover the distance from 0 up to gamma. We can do this integral. The inner integral is y evaluated from x to the fourth to sine x, or just sine of x minus x to the fourth. And then we can do the outer integral, where we integrate with respect to x, and we get minus cosine x, minus 1/5 x to the fifth, and now we integrate from 0 to gamma, like that. Alrighty, and it remains to evaluate these limits, so we get minus cosine of gamma minus 1/5 gamma to the fifth, and then plugging in 0 we get plus 1. Alright, so now we have to figure out what gamma is, and then we can come up with a final numerical answer. So you probably won't be surprised to learn that Sage can actually approximate the solution of this equation. Let's jump over to Sage and do so. It's called the find root function, find underscore root, and just give it the equation, in this case x to the fourth equals sine x, and then tell it where to look for the solution. So all numerical solvers kind of need that extra bit of information. I'm looking at the graph here and I'm seeing that it looks like this solution is between, say, 0.6 and 1. So I'll give it that lower 0.6 and that upper 1. And we get something that looks pretty much in agreement with what we thought. Let's call this gamma. And then let's compute, what do we want to compute? We want to compute minus cosine gamma minus gamma to the fifth over 5 and plus 1. And we get 0.264 approximately. So we can wrap this up by just putting this decimal approximation, 0.264. it's a positive number. That's good. We would certainly expect the area of any figure to be positive. Is it 0.264? I don't know. We're just going to assume that we've done the work correctly, and moving on. Suggested exercises. Again, I want you to do as many of these things as you can. This is a skills-based section. Ignore the exercises that involve probability, and as near as I can tell, there are no exercises that involve improper double integrals, so you don't have to worry about that. Once you've got sort of all of these concepts inside your head, head on over to WebWork and try the assessment for Chapter 5, Section 2. Thanks.